Let's do an example of using the equations of simple harmonic motion in this video. So here's the problem. You have a mass of 550 grams placed on a spring with a spring constant of 50 newtons per meter. The mass is then lifted to a height of 25 centimeters above its equilibrium point. Okay, so reread that, recap it. You have a spring constant of 50 newtons per meter. You put a 550 gram mass on it and bring it down to its equilibrium point. Then you lift that mass up 25 centimeters above that equilibrium point and let it oscillate. We want to know what are the equations of motion, and then we want to find position, velocity, and acceleration at a time of 50 seconds. So here's what we're looking at. Here's the graph of our displacement. We have an initial displacement of 25 centimeters, and it has let me just put these up here. You have a mass of 550 grams, which would be 0.55 kilograms. You have a spring constant of 50 newtons per meter. You have an amplitude of 0.25 meters, and at the end, we're going to have a time of 50 seconds. So those are the 4 bits of information that the problem gave us. Okay, so first of all, we want to write the equations of motion. So this is the equation for position as a function of time. So we have the amplitude, we have the time. We're going to leave time as a variable until the last second. No pun intended. But we need to find omega. How do we find omega? Well, we have 3 ways of finding it. 2 pi divided by the period, 2 pi times the frequency, or we can do the square root of k over m. We don't have the period or the frequency, but we do have square root of k over m. So if we do square root of k over m, and that will be the square root of 50 newtons per meter divided by m, which is 0.550 kilograms. That gives us an omega of 9.535 inverse seconds. Okay, so our equation of motion then would be x is equal to our amplitude, 0.25 meters, times the cosine of omega, 9.535, times your time t. Okay, so there's the equation of motion for position. Let's go ahead and put in our time, 0.25 meters, times the cosine of 9.535, that's inverse seconds, times 50 seconds. This would give us a position of 17.58 centimeters. The calculator came out as 1.1758 meters, which would be 17.58 centimeters. Okay, so let's talk about velocity. With the velocity equation is, velocity is negative a omega sine omega t, and the graph would look something like this. All right, we do know what omega is. Remember that we got that last time. It was 9.535 inverse seconds. There it is. And so our velocity equation then would be negative amplitude, 0.25 meters, times 9.535 inverse seconds, times the sine of 9.535 t. 0.25 times 9.535 gives us a value of 2.384. negative. Negative 2.384 meters per second times the sine of 9.535 t. And so there's your equation for your velocity. Okay, so if we go in and plug in our value of 50 seconds, that'd be negative 2.384 meters per second times the sine of 9.535, again that's inverse seconds, times 50 seconds. That gives us a velocity of 1.695 meters per second, or 1.70 if you're rounding to 3 significant figures. Excellent. Last but not least, we talk about acceleration. So acceleration is going to be the negative amplitude times omega squared times the cosine of omega t, and it would follow a graph that looks like this. So your acceleration then would be negative amplitude is 25 centimeters times 9.535 inverse seconds squared times the cosine of 9.535 t. If I multiply out that first part, I get a negative 22.73 meters per second squared times the cosine of 9.535 t. And there's your last equation of motion. All right, last but not least, let's calculate what the acceleration would be at 50 seconds. Negative 22.73 meters per second squared times the cosine of 9.535 inverse seconds times 50 seconds gives us an acceleration of negative 16.0 meters per second squared. So in summary, we found that omega is 9.535 inverse seconds. The equation for x would be 0.25 meters times the cosine of 9.535 t. The equation for velocity would be a negative 2.384 meters per second times the sine of 9.535 t. And your acceleration equation would be negative 22.73 meters per second squared times the cosine of 9.535 t. So these are your equations of motion right here. Now, we take those equations of motion and we evaluate them at 50 seconds. That gives you a position of, sorry, that should say 17.6 centimeters, or 0.176 meters. You have a velocity of 1.69 meters per second and an acceleration of negative 16 meters per second squared. Okay, let's take a closer look and see exactly what that means on this graph. So a position of 17.6 centimeters, you have an amplitude of 25 centimeters, so that means it's a little more than halfway, something like this, which means it's going to be either at this point or at this point. Is it at 17.6 centimeters going up, or is it 17.6 centimeters going down? Well, those you can see that those are the only two options. You can either have negative slope, which means a negative velocity, or a positive slope, which means a positive velocity. Well, your velocity here is positive, which means that the only time you can have a positive velocity of 1.69 would be at this point here. Sorry, this point. So you would have to have a positive slope. And so that tells us that this is the point that we are looking at right here. So it's this stage of the cycle. Your position is at 17.6 centimeters, and it is at 50 seconds, it is currently rising and moving upward. And the downward acceleration, what's with the downward acceleration? Well, remember that if your spring is going up, that means it's compressed. So you have a force, which is negative kx, opposite the direction of position. But remember also that force is also equal to ma. Force is equal to mass times acceleration. So if you have a positive position, then you're going to have a negative force. And if you have a negative force, then you have to have a negative acceleration. It's a restoring force pushing it back towards the equilibrium point. So even though it's moving up, the force is trying to push it back down towards equilibrium.